This is this quarter's SMPTE Standards Update, and the topic is Uncompressed Video over IP. I am your host, Joel Welch, Director of Professional Development for SMPTE. Welcome to everybody to this quarterly event, and we do have two webcast series that we provide. One is our monthly educational webcasts where we talk about various technical topics, and this is our quarterly standards update where we talk about progress of our standards development committees. Today's speakers are Brad Gilmer. Brad is Executive Director of the Video Services Forum, VSF, and John Dale III, who is President of Media Links. And of course, as always, you've come to listen to our subject matter experts and not to me. So I will hand the floor over to our first presenter, Brad Gilmer. Brad, you're out in the cotton fields of Georgia somewhere, but the floor is yours anyway.
Thank you very much. Yeah, the technology is fairly amazing. I'm between Atlanta and the Georgia coast, and I was telling you earlier, this is the first webcast I've ever done where I'm actually overlooking a cotton field, which is true. And technology is kind of amazing. Anyways, thank you very much, and let's get to it. So I wanted to, before we get it started, I wanted to set the scene, let you know what we're talking about today, and give you a synopsis of what we're going to cover. We're going to talk today about the SMPTE 2022 family of standards, and these, you know, a family of standards or a group of standards is something you don't see too often within the SMPTE. I think we're used to seeing individual standards numbers. The 2022 standard is actually a multi-part standard. And as I said, there aren't too many of them. This is one of them. MXF is another one. What we're trying to do in the Video over IP working group, that's 32NF-60 for those of you that are familiar with the SMPTE technical committees, is we've really tried to group all of these video over IP standards into one group so it's easy to go right to all of the standards that are focused in this particular area. So that's why this is called the 2022 family of standards, and we're going to review that. Specifically, though, we're going to focus today on something called the High Bitrate Media Transport, or HBRMT, and that's 2022-6 and -5, and I'll get to why I refer to them in kind of in reverse numerical order as well. This group of standards came out of an activity group in the Video Services Forum, and I'll give you some history about that and how these came to be. And then John is really going to go into a deep dive into a description of the work and what it enables. A brief history of 2022. This work originally started in a group called the Pro-MPEG Forum, which was another trade association. You might have heard of something called COP3, or Code of Practice 3. And the Pro-MPEG Forum had been working on COP3 and had published the first revision of it with an understanding that really there was some pretty significant work to be done before the work could really be implemented. But the Pro-MPEG Forum decided to sunset, basically go out of business, before that revision could be done. And so the Pro-MPEG Forum was looking for a group that was interested in video over IP transport, and I and some other people in the VSF engaged in a conversation with them, and we decided to take that work over. And so the first 2022 documents, meaning 2022-2 and 2022-1, were essentially the finishing of the work of the COP3 Rev 2 within the Pro-MPEG Forum. So I wanted to be sure that we give credit to that original group that started that work. The 2022 family includes a mapping of video onto IP transport and an associated standardized FEC. Now, why it is that the first number in the 2022 standards groupings tends to refer to the optional FEC and the second group refers to the mandatory mapping document, I don't know. That's probably my fault, but maybe it just wasn't well thought out. But when I say them in this order, like 2022-2, that's the mapping document that's going to tell you how to take video and put it into IP. 2022-1 is a document that's going to tell you about how to do standardized forward error correction, or FEC, and that FEC is really designed to specifically fit the mapping document. Something else I wanted to say, just historically, so that people understand where this group of standards is coming from, is that really the COP3 work focused on taking MPEG-2 transport streams and mapping those into IP. So even though this whole body of work has been called video over IP, I think it's important if you start looking into some of the historical documents, like 2022-1 and 2, that you realize that a lot of that started at MPEG-2 transport streams. And there was a great benefit to that. It really solved a lot of presentation timing issues. MPEG-2 transport streams at this point are very interoperable. And it also resolved how you would handle the mapping of ancillary data and other things, all of those different wrappings and mappings that are already defined in the work that the MPEG-2 effort has encompassed. So with that as a starting point, let's go on to the next slide, and that is really an overview of these 2022 standards. So I'm going to go through these fairly quickly, but I just wanted to let you know why it is that we're going to be talking about -5 and -6 and what came before that. If we start at the top, 2022-1 and 2 really are constant bit rate, MPEG-2 to IP for basically SD-type applications. This was what I was talking about, kind of finishing up the work that the Pro-MPEG Forum had started. So again, just to be clear, the 2022-2 is the mapping of these MPEG-2 transport streams onto IP, and the -1 is the companion FEC. A note here is that it's a robust configurable FEC for short duration outages, and I think that's important. We'll get to a little more of that in a minute, but this FEC does not protect you from very long outages on an IP network. More about that later. So if MPEG-2 is what we're talking about, MPEG-2 can really come in a few different flavors. So we started with MPEG-2 transport streams at constant bit rate. That means that the bit rate is just coming out at a predictable rate over and over and over, basically ad infinitum. Of course, there is variable bit rate MPEG-2, and in that case, the bit rate varies with the complexity of the content that's being compressed. And so 2022-3 is a mapping of variable bit rate MPEG-2 onto IP. VBR actually shows up in a couple of different ways, and I don't really want to get into the details of it now, but it has to do with how the variable bit rate content is presented at the receiver. There's something called piecewise constant VBR and something called non-piecewise constant VBR. And -4 covers the non-piecewise constant version of MPEG-2. And if you want more detail of that, you can look at either one of these standards, -3 or -4, and they'll give you some more information. All right, let's go to the next slide. Now, we get to the concurrent work. 2022-5 is a robust configurable FEC with expanded column and width matrices for the FEC. John's going to talk quite a bit about that later, so I'm just going to put it at that now. But I would say that those expanded matrices needed to be designed to accommodate the much higher bit rates that 2022-6 is capable of handling. So if you look at 2022-6, it's able to handle uncompressed. So for the first time, we're talking about handling full bit rate uncompressed video streams all the way up to the video streams defined in SMPTE 424 at 3 gigabit per second. And so that's very fast. We were looking at using this in low latency contribution applications. As we looked at the FEC, the matrices, the size and protection in terms of the amount of data that was being protected became much larger than what we were dealing with when we started out with our SD application, the original COP3. We do not protect any more time, and we'll get into that in a minute, but over a given period of time, and that's 3 milliseconds, you end up having to protect a lot more data because there's just a lot more data coming down the pipe, and that really was some of the primary adjustments that were made in -5. Those of you that participate in the SMPTE committees might be interested to know that there's currently a ballot open on something called 2022-7. That's seamless protection switching. And this sort of application for 2022 has been focused on transport. And so this technology has been used on high-profile games like NFL and the Olympics and nationwide national broadcasts. And as you can imagine, any sort of hit on those feeds is really a problem. And so 2022-7 is a ballot that's open right now within 32 NF-60. This introduces a technique whereby you can have 2 separate 2022 streams. And it doesn't matter whether these are the older COP3 streams or this newer 2022-6 stream. But so long as your 2 streams meet the parameters that are, the timing parameters that are established in 2022-7, you can take a hit and you can switch seamlessly to the other stream such that you absolutely do not see any disturbance whatsoever at the output of the receiver. So it's pretty simple, the technique, but it's vitally important in terms of meeting the user requirements for these links. Also, I wanted to mention that the VSF has published TR Technical Recommendation 1, which is a mapping of JPEG 2000 and associated audio and ANTS data into MPEG-2 TS over IP, and that's kind of another part of this whole puzzle. So if we look at what our overall goals were for the high bitrate work, we wanted to support 3 video input stream rates, 270, 1.5, and 3 gig, with everything that might come with that. So any kind of embedded signals, data, whatever it might be. We're talking about the entire video signal, including hank and bank. It's all encapsulated as one stream. The video payload is packed into IP datagrams so that for, I believe, for almost all the frame rates, and I think John can answer this, but they make up an integral number of frames. So it's we try to make it very efficient. And as we've talked about before, these different formats come with companion optional FEC. And if you're in a situation where you need to protect for outages, you can use these and they'll be interoperable between manufacturers. When we're talking about transport, and we looked at the issue of protection, a fundamental thing that we recognized was that if you're signing up for a particular quality service with a network provider, that network provider is going to have equipment out there that detects outages and then they're going to switch to a protection or backup circuit. Their router equipment will do something to get you back up. And so what we did not do is we did not design the FEC to protect for some long duration outage. So this FEC works in companion with network protection switching that's typically deployed in protected transport networks. The thing is that it takes those networks a little while to detect the outage and then reconverge and bring the feed back up. And so that's why we've designed the FEC to only cover a period up to 3 milliseconds. And one of the reasons that we didn't just protect for any sort of length of outage was because that protection comes with a cost, and that cost is latency. So the more FEC you introduce, the more protection you introduce, the greater latency you incur between the video going in at a transmitter and coming out at a receiver. So we tried to design this in a logical way where it works with the protection that carriers typically provide, and not create a technology that ends up with latency that's so high that it's basically not usable. If we go to the next slide, again, let's just back up and think about this. What we're talking about is we're talking about encapsulating video and chopping it up into packets and launching it across an IP network. And in order to do that, a long time ago, IP networks were designed, or computer networks basically, were designed to be packet-based and to have different layers of protocols that do different things in the network. So what you're looking at here on the right is the payload itself. So that's the actual 259, 292, or 424 payload. And from there, you've got the you got the payload header with timestamps in there that give you timing information that allow you to present that output at the receiver reconstructed similar to the timing that was present with that content as it came in. We use something called RTP, or Real-Time Transfer Protocol, and I'm going to let John get into some of the detail of that later, but you can think of this as a wrapper and a wrapper and a wrapper and a wrapper. So RTP provides network timing information. UDP provides rules for packetization of content and provides a very simple fire and forget type of transport, compared to TCP, which you've probably heard of. And TCP is really handy for internet, like browser applications, but it's really bad for video because it tries to use techniques like retransmission in order to request lost packets. And with video over IP, we're talking about content that's moving so fast that requesting a retransmission really is not going to do you any good at all. So instead, we use a very lightweight fire and forget type protocol called UDP. And then after that, the networking protocol is IPv4. Of course, you could map this to IPv6. There's nothing that would prevent that. So if we go to the next slide. Yes?
Before we move to the next slide, we do have a question from SMPTE friend Jim D. Philippus.
Yeah. Hi, Jim.
The question is,
go right ahead.
In HBRMTIP, uncompressed encapsulation, is the HANC and VANC data dispersed across the IP datagrams, or is this data segregated to their own IP datagrams, separate from the video IP datagrams?
John Dale, correct me if I'm wrong. I think this is not separated into separate IP datagrams, but we just take the entire frame and pack it up and drop it into the payload. Is that right?
Yes, that's correct. The ancillary data is essentially positioned as if it was video in the SDI. So those video words in ancillary data that are now containing various ancillary audio or ancillary are just transmitted in sequence as you are going across the raster and then across horizontal blanking and back to the next raster. So it's essentially the entire SDI frame that's being transmitted, including blanking. And it's all in the same stream with the same UDP port number, same IP address, same destination address.
Right. So we really tried to keep it simple across all of these family of standards, where when we say we take the whole thing, we really mean it. We take the whole thing. We try not to get fancy with it. We try not to predict what people are going to do with the stuff at the other end. One thing that we need to bear in mind is we keep talking about this FEC, and this FEC is actually sent alongside the payload, the video payload. So it's optional, it's on the same link, but it is a separate stream. And so here you can see you've got the FEC encapsulation with a 3550 header, and then the same stack below it. And again, I'm going to let John talk about the details of that. All right. So if we look at the FEC specifically, the baseline goal and criteria of it is that it really builds on the same FEC we've used the whole process through here. It's an XOR style FEC. Basically, you build a matrix. You've got columns and rows. You calculate an XOR FEC value for each row and each column, and that gets transmitted, and then that can be used to rebuild bits that get lost in those matrices as you go along. As we talked about, the header from RFC 3550 is utilized for RTP, and the FEC header is based on RFC 5109 with expansions, which John can talk about later. Again, we really tried to keep it simple. We tried not to invent anything new. We just tried to describe for our industry how to use existing standards to the greatest extent possible. We've got some additional information about the FEC header. This is really for you to look at later, unless, John, you have something specifically that you want to address here with this slide now. But again, compared to the other slides, we did have to extend this in order to accommodate the larger matrices for the very high bit rates. John, do you have anything else you want to add right here?
Yes, Brad. Just the drawing, the FEC drawing on the bottom just shows that there's three main components. There's an RTP header, then there's a FEC, essentially a forward error correction payload header, and then there's the actual FEC data. And one other point, Brad mentioned that the FEC stream is a separate stream. These are done similar to the 2022-1 standard, where the column FEC, and that'll be shown as L later when we look at the matrices, that would be a UDP port of +2 above the UDP port of the media stream. Then the row FEC would be a UDP port value of +4. So that the receiver, if it's receiving these streams, same IP source destination address, but the UDP ports are +2 for the column FEC and +4 for the row FEC.
And go ahead, John.
Oh, that's fine. That's pretty much what I wanted to add.
Okay, and just to point out, that allows a transmitter to send the video stream itself and then send these row and or column streams to different ports, and a receiver can ignore all of that, or it can take just one of them. So we tried to make it so that the receivers could do whatever they wanted to or whatever was appropriate for their situation. And in the same way, so long as it is kind of previously understood during setup time, a transmitter doesn't have to transmit FEC either. If you have a nailed-up circuit that you know does not lose packets, or you use some other technology in order to ensure that the network is reliable, you don't have to use this FEC at all. All right. So let's go to a slide called High Bitrate Audio Video over IP Description, FEC. Just want to be sure we're synced up since I'm not looking at the internet here. Again, larger matrix sizes were allowed up to 6,000 datagrams. There are some limits in this, and John, I'll let you go over this if you want to later. I'll just point out for anybody who is looking at implementing this or looking at understanding it better, there are limits on these, and these limits are in the standards, and in order for things to work right, you cannot break these limits. And a close reading of this section of the standard, I would suggest, if you're really looking at implementing this, to be sure you get this right. But again, you can see in this slide with the 3 gigabit rate of uncompressed 1080p, we're providing a maximum of 3 milliseconds of protection.
I just want to mention that the offset on the lower left bottom is that is the L value in the FEC, or the column value, and that has been expanded in 2022-5 to 12 bits because that can actually have a value of over 1,000. Where in 2022-1 that was an 8-bit word, so a maximum of 255. The NA value over on the right bottom, that is the depth of the matrix, and that is still an 8-bit value, can be up to 255. So those two, those were changes that were made in the 2022-5 standard to allow for larger matrix sizes than we used with MPEG-2TS.
Yeah, not to beat a dead horse, but just if some people are hearing this for the first time, I just want to cover it one more time, and then John, I'm going to let you take it from here. When we first did -1, we designed the FEC to protect for about 3 milliseconds, because after that we expected that network protection switching would take over and provide protection from there. And we would mask any outage in the meantime while the network protection switching was going on. The reason we've had to expand the matrix to hold a lot more FEC information is not because we decided to go beyond 3 milliseconds, but because during 3 milliseconds, if you're transmitting at 3 gig, you're going to end up chewing up a lot more data than you will have chewed up at SD during those 3 milliseconds. So that's it. John, I'm going to hand it over to you, and I'm going to go on mute until we get to the Q&A.
Okay. All right. Thanks, Brad. Okay, we can move to the next slide. So these are some of the numbers that were calculated, and Brad just did a good job of explaining the forward error correction was thought to deal with short outages that would occur prior to a network protection event occurring. So you can see the fourth bullet down, maximum burst loss protection. At 270 megabits, we were looking, all this is based on 3 milliseconds at 3 gig. So the standard can allow up to 33 milliseconds of protection for SD, up to 6 milliseconds protection of 1.5 gig, and up to 3 milliseconds at 1080p. Since the standard handles all 3 formats, the FEC matrix size was just set up as one size fits all. So on the slower speed signals, you do get a little bit more protection. On the top bullet, you see that the largest matrix size in the standard is 6,000 datagrams, and then that can be set with various matrix sizes. When you see L, that's columns, D is depth. So for a 1D FEC, which is a column-only FEC, and the next slide give you a little bit better understanding of that as we show a picture of it. For column-only FEC, you can have a value of 1 to 1020 for your columns, and the depth of each column can be between 4 and 255. That's for column-only FEC. For row and column FEC, where you're providing 2 FEC streams, one for the columns, one for the rows, then you have a minimum of 4 columns, maximum of 1020, and then a minimum of 4 on the rows and 255 rows. You can't have maximum row and column that will exceed the 6,000 datagrams. It might be possible that vendors will implement FEC beyond this, but this was the interoperability point for the standard. This is what you must support if you support the standard. There's some matrix sizes set for the smaller, or I should say slower speed signals for SD, 1500 packets for HD, 3000, and for 3 gig, 6000. So those are the maximum matrix sizes. One other point that we looked at when we were putting the standard together is that if you wanted to provide error concealment, which is not error correction, but just try to make the errors conceal the errors, make the picture look as clean as possible if you were getting errors. In the media packets, and we'll get to that in a few slides, there's a marker that shows the end of the video frame. So it's relatively easy for a for a receiver to cache an entire frame. If the signal was impaired beyond what the forward error correction could deal with, the receiver could just repeat still frames. So that's a part of the error concealment. Let's go to the next slide, please. Okay, so this slide is showing a picture of a what we would call a 1D FEC stream, where there's green XOR FEC packets for each column. So as this matrix gets computed at the encoder, FEC packets get computed for the vertical packets and get interleaved with the transmission and sent. So in this case, if we look at this, we have a 20 column FEC. This would provide a burst loss of a maximum of 20 packets in this current configuration. Some of the values that are up here might make a little bit more sense now if we look at the picture. So now we see the D values are the columns, the L values are the columns, the D values are the rows. In this case, we have 5 media rows and 20 columns, and we have 20 FEC packets. The burst protection that's shown there is based on burst protection is always based on the maximum number of columns. So in this picture that you're looking at, you have a protection for 20 columns. If you were to expand out the columns to the maximum 1020, that would give you 1020 burst packet burst loss protection. Okay, this is an example of 1D. We're going to move to the next slide and we'll show you an example of 2D FEC. So 2D FEC provides the same column FEC that we showed in the last slide, but now you also have a FEC that's computed on the row. So the green packets across the right, each one is computed across the row. In this case, and what's useful about this style FEC is that you can have burst loss protection with the column FEC, and then you can also have random packet outage that's covered by the row FEC. And if errors were distributed evenly, you could actually have two errors in a specific column, one protected by the column FEC and one protected by the row FEC, because this is an even matrix that you're looking at. But that's how FEC can be applied. Generally, we see usually on good performing networks, packet loss is sort of random and fairly low. So a very light FEC is required. If you have a noisy or dirty or bad link where you're having lots of errors, then a 2D FEC might be required. And that gives you more coverage than a 1D FEC. However, the trade-off is that in this case, our FEC overhead is double what a column-only FEC would be, since we have both column and row FEC. So you have a higher overhead for your FEC, and the matrix size is slightly larger, so you have a little bit more latency. But the forward error correction is tunable based on your situation. You can tune for the amount of overhead that you can tolerate and the matrix size, smaller or larger. Larger is more latency, smaller is less latency. So the standard allows tuning of that based on the selection of 1D or 2D FEC and the size of the matrix. Okay, we can go to the next slide. So now we're going to talk about the encapsulation of the media, the SDI, HD-SDI, 1080p SDI signal. We looked at this slide earlier. This is showing us the payload, which has a payload header, a RTP header, and then an IP or UDP header and an IP header. In the bottom part of this picture, we're using RTP. That gives us the ability to reorder packets. The RTP header has, we'll get into the next slide, it has sequence numbers on the packets, so we know what order the packets are in. It also has a timestamp that will help us in reordering packets if there's rollover on the sequence numbers. We have a payload header that we put in specifically to help us with some information about the video payload. And then we have the media itself. And the media itself, we're using 1376 octets for the media. So our packet size is constant. The media packet size is always 1428 bytes. So the constant size packet, and because it's CBR, the packets are sent from the transmitter at close to a constant rate as well. Okay, we can go to the next slide. So I started with the RTP header, and this is RFC 3550 header. A few of the values that we want to talk about. The M marker bit, which is the in spot 8 there, is important because we're setting that to mark the last datagram of the video frame, and we have an integer number of datagrams for each one of the video formats, so that marker gets set. The receiver can tell when the end of a frame occurs by looking at the header without actually diving into the SDI video. So that's an important piece of the standard. We had looked at Code of Practice 4, which the Pro-MPEG Forum was working on at the time, that was marking individual lines with end of line and having an integer number of packets for each video line. However, this standard was looking to handle video formats from 270 megabits to 1.5 gig to 3 gig. There's many more formats, and we thought that having the markers change for individual lines would make implementations rather complicated if they wanted to support many formats. So this was sort of a compromise position where we said we would mark the end of the frame but not the end of the video lines. Okay, let's go to the next. So, this is continuing with the RTP header. There's we used a fixed payload type for the definition of the stream, and there's two types that were that are being used. 98 is for the video stream itself, and payload type 99 is for the FEC stream. So a network sniffer or analyzer could look at the packets, read the payload type, and say, okay, this is uncompressed video, or this is an FEC stream. So I mentioned before that the FEC streams just have a different UDP port, but they also have a different payload type. The frequency of the RTP timestamp in the RTP headers that are used for 2022.1 and 2, that's a 90 kilohertz clock frequency. In this case, because the speed of the signal was faster, we wanted to use a higher frequency timestamp. The one of the reasons for doing that is that Brad mentioned that there's a standard about seamless switching. In seamless switching, you may be buffering two streams and that are much different in time, but started from the same source, and you buffer them to match the sequence number. In this case, we can use the sequence number. If the sequence number has rolled over, we can use the timestamp value and the sequence number to line those up so that we can do timed seamless switching between them. So that's important. That that's part of the RTP header. Okay, we can go to the next slide. So this gets into the definition of the media datagram payload header. So we talked about the RTP header. Now we have some information about the video that we're carrying. There's a few fields here, and these are spelled out with lengthy definitions or clear definitions in the standard itself. One thing about the payload header is that we put the ability in to extend it with possible revisions of the standard, so that if there was use for this for other types of media or new formats or other closely related applications, that it could be extended. So there's information that not only in the RTP header it says if there's an extension or not, but here it says how long the extension would be in the first 4 bits. There's also information about whether or not there is a video timestamp, whether or not the stream has a protection applied to it, if it's a primary stream or a protected stream, whether it's locked to a universal clock reference. The FR count is an 8-bit value that increments per frame, so all of the integer packets for a specific video frame would have the same FR count value. As we increment to the next frame, they would have an incremented FR count value. So you can see what frame in order the packets are from by looking at the frame count value. There's a bit that could tell you that the payload is scrambled or non-scrambled. That's the S bit. There's FEC, which says what type of FEC is being sent along with these packets. It's not included in this packet, but it could tell the receiver that, hey, you should be looking for some FEC packets because they should be coming along. Clock frequency for the video timestamp. There's a few different values that video timestamp can be, and the CF value tells you what value that is. There's a second page on this we can move to that has a little bit more information on that header. This was a challenge for us because the original 2022 standard included essentially just taking the SMPTE 352 format information from the SDI and putting it into the payload header. But we received some information that was not highly reliable, so we created a table within the 2022-6 standard for describing the content that was going to be in the payload. So in this case, we have separate areas for map, frame, F-rate, sample. And the map describes whether it's direct or dual link. The frame gets into the horizontal and vertical scanning, progressive interlace. The rate gets into the frame rate, and then the sampling 422, 444, etc. Is defined there. So in this case, a compliant device would read the 352 or figure out what the incoming video is, and then it would take that information and put it into the payload header so that it would tell the receiver exactly what the content was. And then at the receiver, it'll take this information. It could take the information out and put it into the 352, or the 352 could be transported across in the ancillary space as is. And we reserve some space that if there's some formats in the future we want to support, we need some additional information, we have the ability to do that. There's the video timestamp, and then the header extension on the bottom of this that could be put into place if there's some later use for it. Okay, we can go to the next slide. So we talked about the RTP header, the payload header. Lastly is the payload itself. And the nominal payload is 1,376 octets. This is the chroma and luminance values of the video, and they're put into the payload. There's an even amount of values per frame, but as you're putting the payload in, where you end with values in one IP packet, you just start in the next one until you get to the end, and then depending on the format of video, the last payload of the frame will have some empty space, or if you want to call that padding or reserved. The last IP packet of the frame will not be full, and that depends on the exact format that you're sending. So the payload includes the 10-bit or 12-bit samples of luminance and color difference as defined by the table that we have in the header, and then the sample words are carried in their original format. They're not NRZI encoded as they are in SDI. They're in the original format. Ethernet has its own scrambling, which is used to make sure that transitions can be picked up at the receiver. Okay, we can go to the next. So I wanted to just make a couple comments on what, if we look at the payload headers in the IP domain, what can we figure out about the payload itself? So from the standard, it allows us to look at the payload headers and determine the video format, the sampling, and the frame rate. We can also find the start of the frame and the end of the frame, which is an integer number of datagrams. The frame counter sequence is up to 256, so we can see a sequence of 256 frames before it rolls over. and the datagram size is constant. So that's what this allows us to see in the IP domain without looking into the IP payload header. I'm sorry, without looking into the IP payload itself. What is not known is that we don't know the specific video line, and data, the payload data may cross the line barriers within the same IP datagram. So you may have information from two different lines in the same payload. You do have RTP sequence numbers, so we can reorder packets at the receiver. Unlike a UDP stream with RTP, we can reorder. So if packets get out of order in the network, as long as there's enough of a buffer on the receiver, we can reorder them. Okay, so I think the last slide here, and I just put this in here, this was part of the standard for a little while, and then we removed it, but it just shows the number of formats that are supported in the SMPTE standards. And if you look at the number, this is the second to the last column on the right. It's a little bit of an eye chart if you can read it, but this is the number of IP datagrams per frame. So you see that number changes depending on the formats. However, you can, based on this knowledge, you know how many frames, how many IP Ethernet frames it will take to make up a video frame. So that's the list, and there's a number of formats supported. If you're using this equipment, you probably want to check with the equipment manufacturer to make sure the type of video that you want to transport is supported. This standard provides support for many formats, and it's not mandatory that a compliant piece of equipment supports every single format. And unlike an SDI pipe that runs at 270 or 1.485, there's nothing different between the formats. Here, the IP encapsulation and the markers that are placed in the end of frame change with every format. So that format has to be specifically supported. Okay, I think that concludes the tutorial.
And it does. With that, I invite our guests to submit questions to our speakers. We have a few minutes for questions, and you can do that by using the chat or question box. And how long has this standard been in the works, Brad or John, as we're waiting for questions? When did work begin?
I'm trying to remember, John, in the 90s sometime, right?
Well, you know, we first started with some ITU work late 90s. I think the work on this standard started in 2006 on this specific work. I could be wrong by a year or two. It took a while.
Okay.
Yeah,
longer than we thought.
Yeah. One other thing while we're waiting for questions that I would mention is that this standard is specifically written for long-haul transport. And there's now a joint task force on network media that's looking at video over IP in the studio. And we're looking specifically to support as seamless a transition as we can between this mechanism used to transport content between facilities and whatever we might do that's extremely low latency and might actually provide no error protection, which would be used inside a facility. So if you're interested in this area, just be aware that this is work that probably will inform what the Joint Task Force does ultimately in terms of recommendations for inside a facility, but that's not really the concentration of this standard.
Great. And we do have a number of questions in the queue. The first of which is from John Grant, asking, how are the 10-bit words packed into bytes?
They're essentially packed across bytes, and there's I probably best to recommend reading the standard. There's actually some drawings in the standard that explain that, and that's probably the best way to take a look at that. I mean, there is definitely go from 8-bit from 10-bit to 8-bit, but we don't do the bits are just set across. They're not. We don't do word calculations. Okay.
And we do have a question from someone who just had to leave the meeting, but I'll ask the question anyway. What applications and or use cases will be addressed by this new transport standard?
We've seen applications that sort of run the gamut, but at the moment it seems like large sporting events have used this technology, both in metro, and we're actually seeing some long distance networking using this technology, although it doesn't use compression, so it uses fairly high bit rates, but there are applications that are using it for live events with uncompressed transport.
And I think we also see it used in conjunction with other technologies that like file transfer accelerators and so on. So one of the handy things about this for companies that have dark fiber or high bandwidth connections between facilities, that they may ensure they have the correct QoS parameters set up to run this, and then they may run file transfer alongside it, or they, at times that links are not used for this application, they turn that down and then turn up file transfer or other IP, conventional IP applications.
Great. We're at the top of the hour, but are you gentlemen available to answer 1, 2, 3, 4, about half a dozen more questions?
Sure, absolutely. And also, just before we start losing people, I just want to make one other thing clear for folks. Unfortunately, as 2022-5 was prepared for publication, a draft version of that document somehow got into the publication pipeline. And so if people take this presentation and then they go right this minute, I believe, Joel, and download 2022-5, they're going to find, if they start looking closely, some anomalies. I mean, most, I think egregiously, L and D were flipped. The description of what L means in terms of a row and D means in terms of column and row, those were flipped. A new version of 2022-5, colon 2013, is approved, and I believe it's going to be posted on the SMPTE site for download and purchase any day now. So just for listeners who are going to do a deep dive into this, please be sure when you look at the FEC component that you've got the 2013 version of that.
That's good information. Thank you. Next question. Is it envisioned that routers will support the 2022 FEC in regards to monitoring as well as protection switching, or is this just for endpoint recovery?
That's a pretty good. That's a pretty good question. At the moment, from doing several interops, I would say that it's just endpoint right now. What the future holds, I mean, that's one of the beauties of having standardization, that this could get built into other devices, midstream, wherever you might have in the network. We haven't seen that yet. One of the larger routing companies that actually supports a line of video products has not had a compliant 2022 implementation yet. But that might be something that you'd want to ask those. I mean, there's a standard they could do it.
Thank you. Next question. I assume you're looking at 4K for the future. If so, what type of mapping? Quad link? 2.6G?
Yeah, that's a good question. We haven't got a specific user request for that yet. And, you know, there's been debate within the Video Services Forum, the trade association. There's been a lot of discussion about, you know, would people ever really use 4K for transport? Right now, you know, there hasn't been a particularly strong end-user proponent for that, but, you know, I don't think it takes a rocket scientist to see that that's, you know, that the potential is there for it. John, go ahead. I think you have some comments too.
Yeah, so because we've seen some of this done, I think there would be two ways to do it, and one thing is that we definitely through VSF, through SMPTE, we would like to, if these formats are required, we would like to get that input so that it can be applied to the standard. It would probably make sense to do it as a single IP stream that includes all of the data, whether you come into it with multiple links, with perhaps 4 SDI signals into your encapsulator. You would probably want to take those 4 streams and put them into the same IP stream so that the timing relationship between them could be maintained through the network. I think that would be advantageous to do it that way. But we would definitely need a proponent to work through that and get it put into the standard.
And John, I have one other thing to pitch in here, just along those lines, which is kind of a for me, just speaking personally, having worked in professional video for quite a long time, you know, you always had the concept that if you start out as 270 megabits at the end of a piece of coax, you're going to come out 270 at the other end, and so on, right? And if you go in at 3 gig, you know, as a single link, you're coming out that way. The potential for this standard and other video over IP standards at large is it's really a game changer. You can imagine a field camera that's designed to come out with this stream right at the output at the back of the camera. And so once you do that, how that content is instantiated at the other end is totally independent of how it started out. And that really is a different way of thinking about content. And it really, this represents a hard break between kind of the physical connector or connectors that are on the back of a piece of equipment and how it starts out and how it ends up. So just because it comes in as, let's say, 4 3 gig links, who knows how it'll come out on the other end, and that's you know, it's absolutely within the realm of possibility that it could come out in several different ways.
Thank you. We do have a number of additional questions, and but we are starting to lose people. I'd like to ask one more question, and then I can forward these questions to you, gentlemen, and you can answer them offline and send the responses to me, and I'll distribute them if that works for you.
Sure, no problem.
Okay. And then our final question is, what is the relationship of 2022 to IEEE's 802 AVB?
That's a good question. So if you look at the question of how are we going to transmit video as packets across a network, then the answer to this question is that these are different tools in a toolbox. So it's like you dig in your toolbox, and you know you got a screwdriver and you got a hammer, and you use each one for the appropriate job. AVB operates at layer 2, so that means it's Ethernet kind of base technology. And this technology is a layer 3 or IP technology. There's all sorts of kind of pros and cons about that, which I don't know that we want to spend a lot of time getting into here, but they're really kind of different tools solving different problems. This particular tool is very much about solving the problem of moving video and audio across long distances. AVB is very much about providing very low latency, very tightly timed, down to nanosecond timing, transport of video within a small area, maybe around an audio post-production facility, or actually for amplified speakers, building a phased array amplified speaker setup. The thing that we want to ensure as an industry is that there's a reliable way to get from one to the other, and that certainly is on the radar of this joint task force that we talked about. John, do you have anything else you want to add to that?
No, I think that was actually a good description. There are different tools in the toolkit. The purpose of this was for WAN style connectivity, and AVB has been really targeted at within the studio, within the campus at maximum. So, and yes, the Joint Task Force is an area that is going to look into this really specifically.
Excellent, excellent. Well, thank you very much, gentlemen. I do appreciate you taking the time to put together the slides and present to our guests. I do also want to thank our guests for hanging in there with us for the time that we've had. It's been a little more than an hour. So thank you to everybody. Brad, John, Brad, safe travels. Sounds like you've reached your destination. And John, thank you for participating. Everybody else, we'll see you next time on our SMPTE Standards Update webcasts, and hopefully on SMPTE educational webcasts that we have on a monthly basis. With that, thank you for your time and support. Take care and have a good day.